Okay, so as I said, good afternoon, everybody. What I want to do today is I want to pick up right where we left off last time. And if you remember what we were doing last class, is we started this topic called discrete random variables. Okay, and we talked about this concept of a probability distribution. And I don't know if you guys remember, but we did a probability distribution for a die roll, and then we talked about the number of cups of coffee that I have. I actually have one right now, so add that to the list. So I'm going to pick up there, and that'll take us maybe the first. I want to introduce a topic called expected value, and that's going to take us the first part of class. That'll take us right to break, and then when we come back from break, we'll introduce something called the binomial probability distribution. Okay, so just another reminder, homework number 3 is posted in the classroom. It's right here. That's due next Tuesday. How many people who are here right now have started this? How many people have given it a good go? Melissa has, great. Anybody else? Okay, a few people have. So actually what I want to do today is, I'm not going to take any questions on the homework today. What I want to do is next class, I'll take as many homework questions as people have. Okay, because this is a really good way to study for the exam. Okay, so by the end of class today, you'll definitely be able to do number 8, and you should be able to get started on question number 7. Okay, you don't have a midterm, you have 4 exams, and your next exam is next Tuesday. Yep. So you don't have a cumulative final exam. You have a last exam, Jamie. If you guys look back over the syllabus, right, there's 4 exams in this course. I drop your lowest exam from the first 3 exams, and then everybody has to take the last exam, and the last exam cannot be dropped. But there is no cumulative midterm or cumulative final. I could make one. Do people want one? That's okay. I didn't think so. No, thank you. Yeah, no problem. And so next Tuesday we'll have our next exam, and I know I've said this before. This tends to be the hardest exam. Students tend to do the worst on this exam for whatever reason. So when I'm not saying that will happen to any of you. I'm just saying from past experience, that's just generally what happens. Not for everybody, just on average. So don't be stressed about the exam all that much. Or if you score low on it, I wouldn't stress too much. And then also I've posted some old exams in the week 6 folder. So if you go to course content under week 6, you can find some old exams. Okay, so you can see generally what type of questions I ask. All right. So save your homework questions for next class. Please start the homework. It's a lengthy homework, and definitely take a look at it before Thursday, so in case you have any questions for me. All right. Anyways, before I get started, does anybody have any general questions about any of that? No questions? Ready for class then? Okay. All right. So I actually like this next topic. I think it's a rather interesting topic. And I think there are some cool examples that I have for this topic. And what this is called the mean. So, the mean, we know that that's synonymous with an average of some type. So the mean of a discrete random variable. Okay. So let me give you the definition of this. And it goes like this. The mean, or what it's also referred to as, or it's also called the expected value. So the mean or expected value for a discrete random variable X. Okay, and remember what discrete random variable is. I'm just going to go back real quick. All right. It's a quantitative variable whose value depends on chance, and there's a finite number of possible outcomes that could happen. There's a finite number of things that could happen. Okay, that's important. Okay, so the mean or expected value for discrete random variable X is given by we use the Greek letter mu with a subscripted X. Okay, so this means the average of the variable X. That's what that subscripted X is. Okay, mean of the variable X. And it's like the super simple formula for this class. It's this operator first. Does anybody remember what this stood for in this class, or what this was the sign for?
Sum.
Yep, it's the summation. You take each X value and you multiply by its corresponding probability. So you take each X value, multiply by its given probability, and sum it up. That's it. Okay, that's all you need to do. So that seems pretty straightforward. And I promise you, after we do one or two examples of this, you'll be like, oh yeah. Okay, Matt, that's fine. That makes sense. So let me give you kind of like the interpretation of this, what exactly it is for a mean or expected value. Okay. So this mean or expected value can be considered the long run average. So a long run average of the random variable in repeated independent observations. Okay, what the heck does that mean? And I think after we do the first example, it'll make sense what I mean by this long run average of the random variable is these repeated independent observations. So I've got 4 examples picked out for this thing here. And is everybody okay if I go to the next slide and just like jump right into the examples? Wait, yep, no problem. I don't mind. Let me know when I can go on, Alexandra. Okay to go on, or? Okay, good. All right, so we've got this formula and this expected value or this mean, and we're calling the mean this long run average. All right, so here's example 1. Let's find the expected value of a die roll. Okay. So what this means, or the interpretation of this expected value, is it's a long run average. Right, so imagine I'm going to roll a die. Okay. What are the values on a 6-sided die that can come up? 1 through 6. Yep, 1, 2, 3, 4, 5, 6. So the first time I roll this, it's a 1. Then the next time I roll it, I get a 3. Then I roll it again, I get another 3. Then maybe I keep going. I keep rolling. Okay, I'm just going to keep rolling the die, okay? And I'm going to look at my result. And then what I would do is, to find this expected value here, is I would take the average of all my die rolls, okay? So this long run average would be the average of all these die rolls. That's all this expected value is. It's like if you were to keep rolling a die over and over and over and over and over and over and over again, like what would the long run average be? Okay. Does that kind of make sense? And if I were to keep rolling die, rolling, what would the average of all my different die rolls end up being? That's what this means. Like, does my average die roll converge to some number? That's what this expected value is. Okay. Okay, so to do this, to find this expected value, you need to find or need the probability distribution for a die roll. So if you look back here, I'm going to go back real quick. We actually did that. Okay. Do people, if you could let me know in the chat, do people remember writing out this probability distribution for a die roll last week? We listed the values of that X could take on the die roll. And then I listed their corresponding probabilities. Somebody give me a shout out in the chat if they remember it. Melissa does. Does anybody else kind of remember this? Maybe let me know so I don't think I'm just talking to myself here. I appreciate it. Thanks, everybody. Okay. So what I'm going to do is I'm going to rewrite the probability distribution. So what the probability distribution did is it listed the values of X. So the die roll could take on 1, 2, 3, 4, 5, and 6. And their corresponding probabilities were 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. All right, so this expected value here, it's equal to the sum. You're going to take each X value and multiply by its corresponding probability. All right, so each X value times its corresponding probability. So this is super easy to do, okay? This is equal to, so you're going to take 1, multiply it by 1/6, and then you're going to add to it. You're going to take 2 and multiply it by 1/6, and you're going to keep going. Okay. So now all we have to do is just figure out this arithmetic here, okay? So 1 times 1/6 is 1/6 plus. Can anybody in chat tell me what 2 times 1/6 is? Bum, 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 bum. Yep. Yeah, so I'm actually not even going to reduce it. So it would be 2 times 1, so it'd be 2/6, and you'll see why I don't reduce it, but that's actually the answer. So 3 times 1/6 is 3/6. 4 times 1/6 is 4/6. 5 times 1/6 is 5/6. And 6 times 1/6 is 6/6. The reason I didn't reduce it is because now they all have a common denominator. So look, 1 plus 2 is 3, 6, 10, 15. This is 21/6. Can anybody with a calculator tell me what 21 divided by 6 becomes? Yeah. Okay. So this is weird. Okay. So what I'm saying here is the following. This is the correct answer. I'm saying the long run average of rolling a die repeatedly over and over and over and over again is 3.5. But now here's the thing. Okay. Can you actually roll a 6-sided die and have the number 3.5 come up? Like, can you roll the die and have it like, oh, it lands perfectly between 3 and 4? No, you can't, right? Like, that's not a value you can get. We didn't do anything wrong, though. That's the right answer. And like, here's why. So consider this. If you have 2 students take a score and one student gets a 60 and one student gets an 80, all right, what is the average of those 2 test scores? I think it's a 70, right? So like, that's still the average. Did any student who took the exam actually score a 70 on the exam? No, right? But that's still the average of those 2 numbers. So it works the same way here. Another thing that's really interesting is, do you guys remember the casino game we talked about a couple lectures ago? It started with a C. Anybody remember that? It was the game of craps. Yep. So it turns out this is wild. Okay, when you play the game of craps and you roll 2 dice and you sum the results, the number, the sum that comes up the most when you roll 2 dice and sum the results is the sum of 7. Okay, so that sum will come up more often than any other sum. Okay, but now this is wild. Like, if you roll 1 dice in the long run, the value is 3.5 on average, the long run average. You roll another die, the long run average is 3.5. 3.5 plus 3.5 gets you that sum of 7. So like, this all makes sense in the long run. This is just a long run average. Okay. All right. Well, let me ask you this: is the formula okay? Formula pretty straightforward. At least the formula is easy to follow. Okay, not bad. All right, so here's what I want to do. I just want to do one more like very simple example, okay? And then I'm going to do 2 real world examples so you can see like some uses of this, okay? Everybody okay if I go to the next slide? Everybody good? Okay. Let's go back and do the find the expected value for the number of cups of coffee Matt has per day. So I gave you this formula a while ago. So I'll come back to this slide. But if you look back, I gave you this probability distribution the other day, right here. This was the number of cups of coffee I had. So it was 0, 1, 2, 3, or 4, 0.5, 0.15, 0.2, 0.3, 0.3. 0, sorry. 1, 2, 3, or 4. And the corresponding probabilities was 0.05, 0.15, 0.20, 0.30, and 0.30. All right. So if I wanted to find the expected value of this, you just follow that formula. Mu sub x is equal to the sum of each x value times their corresponding probability. So look, this is really straightforward. You just take the value of x and multiply by its probability. So you take 0 times 0.05, and then you would add to it, because it's the sum, the next one, 1 times 0.15, plus 2 times 0.20, plus 3 times 0.30 plus 4 times 0.30. So now once you have this set up, you just have to do the arithmetic. Okay, it's 0 plus 0.15. 2 times this gets you 0.40. 3 times this gets you 0.90. And 4 times this gets you 1.20. Thank you, Melissa. Yeah, if you were to add all these numbers up, this is what they would say. Look, Matt, your long run average for the number of cups of coffee you consume per day, in the long run, on average, I consume 2.65 cups of coffee a day. I think I have to adjust this because that seems a little bit low, to be honest with you. I'm not saying I have a coffee problem, but it's pretty evident based on this. Okay, thank you for the laugh there. I appreciate that. Okay. So what I want to do now is I want to give you some real world examples where you're not given this probability distribution. Okay. I want to give you 2 examples where, and this is an example. One of these is going to be like an example on your homework. And then you're going to have an example like this kind of on your exam too. Okay. So in these first 2 examples, like I give you the probability distribution, but now these next 2 examples, what we're going to have to do is we're going to have to figure them out. Okay. And that can be a little bit hard. Okay. But also more fun, I think. Everybody okay if I go to the next slide here to do this next example? Can you just show the first one real quick? Yeah, of course. This one right here. Okay. Are you good? I can move on? Okay. So I want to do another casino game example here, okay? And I want to do the game of roulette. I'm just curious, how many people have heard of the game of roulette before? Yeah. Let me just show you what the roulette wheel looks like real quick, in case you haven't. So roulette's this game, and there's all different ways you can number the roulette wheel. I'm going to simplify it very easily for you. So it's this game where they have this wheel and they spin the wheel. Everybody can see it right here. They spin the wheel, and what they do is they drop a ball into this wheel, and it spins and spins and spins and spins and spins, and then it lands on a number, and that's the winning number for the round. Okay. So maybe you haven't, been, I don't know how to say this, maybe you haven't been in a casino, right, and seen this, but maybe you've seen this on like television shows or something, I always feel like there's always some movie where they go bust up a underground casino or something and everybody's playing roulette. Okay. So what I want to do here is, have you guys always heard this saying, if you have, the house always wins? Have people heard this saying before? The house always wins. No, you haven't heard this saying before? Anybody has? Anybody though? What does the house always win mean in terms of casino? You can turn your mic on, Melissa, if you want, or I can explain it.
It's like that the odds are in the house's favor. That's my understanding.
That's exactly it. Okay, so There's this saying like when you go to the casino is like the house always wins, man. Like, you know, you can win some money in the short term, but in the long run, the house will always take your money. Okay. And so what I want to do is I want to explain that to you using the game of roulette. Okay. Why, like when you go to the casino, or how casinos make money. Okay. So let me just simplify the roulette wheel for you. Okay. So the roulette wheel, the roulette wheel. Okay. If you look at it, okay, there's different types of roulette wheels. There's an American wheel. There's a European wheel. So you can see the subtle differences in them. Okay. But we're going to talk about the American wheel. Okay. The American roulette wheel. So the American roulette wheel has 38 numbers on it. Okay. This isn't exactly the case, but if you look here, you'll notice that some numbers are red and some numbers are black. Okay, so to just simplify it, let's just say the numbers 1 through number 18 on the wheel are red numbers. And then the numbers 19 through numbers 36 on the wheel are black numbers. Okay. I'm just curious, does anybody know what other two numbers there are on a roulette wheel? Let's see if there's any gamblers in the chat. Yep, there's 0 and there's another one, 00. Okay. 0 and 00, they're called. And these are what also referred to as the green. Okay, green numbers. I got yeah, never mind. Just I think I've told you guys I used to live in Las Vegas, so just some memories come to mind here. Okay. Nothing I should share though. All right, so if you look here, thanks. Yeah. So there's this very there's this very common bet you can make on the roulette wheel where you can bet that a color is going to come up. Okay, so you can bet that all the red numbers are going to come up and all the black numbers. You bet red, it means if a red number comes up, you win, or you can bet black, and if a black number comes up, you win. So what we're going to do is we want to compute the expected value of a $10 bet on red. Okay. So the way this works is if I bet $10, okay, on a red number coming up, and a red number does come up, I win $10. So if a red number comes up, I win $10. Sweet. If anything else comes up, how much do I lose? What do I lose? I just lose my $10. That's it. Okay. So now it's up to us. I've given you enough information here. It's up to us to figure out the expected value of a $10 bet on the red numbers. Okay. So whenever a problem on your homework or on an exam says expected value, you're going to need to write out the probability distribution here. Okay. All right. So from the casino's perspective, or even from my perspective, okay, if I have a $10 bet down, what are the two outcomes? I can either win the bet, or what else could I do?
Lose.
Yep, I can either win or lose. That's it, right? So I can win the bet, sweet, or I could lose the bet. All right, well, look, if I win the bet, I get $10. Nice. If I lose the bet, I'm going to lose $10. So I would have negative $10. Do you see how I need that negative there to signify that I've lost my $10? Okay, that's important. So now here's the hard part, or maybe not, okay? I'm betting on red, okay? So just so we're clear here, let me define what X is. I should have done that here. Let's let X be equal to the amount won on a $10 bet on red for a roulette wheel. I'm sorry, I should have did that first. Okay. And look, the amount I win or lose is obviously determined by chance, and there's only a finite number of things that could happen here. That's why this is a discrete random variable. Okay, so what's the probability I win? Now, this is the hard part. Can anybody tell me what the probability is I win on a roulette wheel, on a bet of red? Yeah, thank you. Yeah, how many red numbers are there? Look, it's the red numbers 1 through 18 right here. And then there are 38 total numbers. So the probability I win would be any of the 18 red numbers come up out of the 38 total other numbers. Okay, so now what's the probability I lose? Well, do I lose if a black number comes up? Yes. Do I lose if a green number comes up? Yes. So how many black and green numbers are there total? Yeah, there's 18 black numbers and then 2 green numbers. So this would be 20 out of 38. So now look, now I can figure out what the expected value is. Mu sub x, it's the sum of each x value times their corresponding probability. So we take 10, multiply it by 18 over 38. I would add to it negative 10 times 20 over 38. And check this out. This becomes 10 times 18 is 180 out of 38 minus 10 times 20, so minus 200 out of 38. This ends up being minus 20 out of 38. Just grab a trusty calculator here. So when I'm just going to round this to 2 decimal places, it's 0.53. So it's minus 0.53. Okay, so to put this in perspective here, what this means is every time I do this $10 bet in the long run, every time, on average, I'm going to lose 53 cents for that $10 bet. Is that good for me or good for the casino? It's really good for the casino. Yeah. And this is how they make their money. Okay. They don't care if people win or lose a single game. That just has zero meaning to the casino. What they know is that, look, we're going to keep spinning this wheel 24 hours a day, 7 days a week. And every time it spins, the players in the long run are expected to lose money. And I'll tell you this, any game that you go to in the casino, in its initial state that the game starts in, because I know that you can like count cards and blackjack and stuff, but like in the initial state, every single game at a casino is negative expected value for the player. So you should, I'm not saying you should ever go to a casino. I'm not saying that. But if you do, you should never expect to win money, because in the long run, you'll always lose. A little bit interesting. A little bit.
Professor, one quick question.
Sure.
Again, how did you get the 20 out of 38? Because I see that there's like 19 that are black, and then like I don't know where you got that other one.
So 19 through 36, there's 18 of them. And then the 2 greens, so 18 numbers here, and then 19, and then the two double zeros are 20.
Oh, okay, thank you.
Yeah, because also you could also do it this way. If there's 18 red numbers and there's 38 total, that means there's 20 other numbers. And don't worry, I would never do a casino game example question on a homework or a exam. Okay, I just do them in class because I think they're really good at illustrating the concepts. Okay. Right, so what I want to do next, I want to do an example of a question that's on your homework, and then a question that I always like to ask on an exam. Okay, so if this one was a little confusing here, let me hopefully do this next one, and this next one will be make a little bit more sense. Okay. So is everybody okay if I go to the next slide? Everybody good? Okay. So this next one also mirrors on your homework. Like if you go to your homework, I think it's question number 8. So after class today, you could do question number 8. I'll also ask a question just like this on the exam. Okay. So, if you weren't paying too much attention, you should definitely pay attention to this next one. And this is about what's called a term life insurance policy. Okay. So what we're going to do is we're going to price what's called a 1-year term life insurance policy. Can anybody tell me what's meant by a 1-year term? Like we all know what life insurance is, right? So what is a 1-year term life insurance policy mean? Anyone have a guess? No guesses. So all of 1-year term life insurance policy is you buy the life insurance policy and it's good for 1 year. That's it. Okay. Like your life insurance policy lasts for 1 year. Okay. So if you live or die within that 1 year, the life insurance pays out or it doesn't pay out. And then after the 1 year's up, your life insurance policy expires and you'll have to buy another one. Okay. So it's just like you have protection for 1 year. That's all this means. Okay. So let's suppose that I have a life insurance policy. Okay, so Matt purchased a 1-year term life insurance policy for $1,000. Okay. And it pays out $250,000 should Matt die. Okay. It's a little bit of a morbid example for me. Okay. So what I want us to do, okay, is I want us to price this policy out. Okay. But we actually need a little bit of information here. Okay. If you look back here, okay, there's some X values here. Okay. And I'll explain that some of these X values are listed here. But, oops, sorry. I always give you like these probabilities. Okay. If you look here for like all these formulas, you need a probability. Okay. So to answer this question, can anybody tell me what I need to know the probability of for me? And I'm going to knock on wood because this is a pretty morbid example. Good. No takers?
Didn't we do something similar like this? It was like 0.97 probability that someone your age would live.
Yeah, okay, that's right. So I have to figure out the probability that I'm going to live or die, and it's really really sad, scary. But so spell today. So you can look up these things called actuarial tables, and I'm just curious. Has anybody ever heard of an actuary before? So an actuary is it's a very good career. It's a mathematician who prices risk. And so there's these things called these actuarial tables. And if you look here, the most recent year they have is for 2017, but they have it for a male. And if you give their exact age, and if they're a healthy individual, it gives the probability that they're going to live or die. Okay. So if you look here, I'm 39. So the probability that I'm going to live to be 40, okay, is or the probability I'm going to die, excuse me. The probability that I'm going to die within the next year is 0.002, okay? And it's a little scary. It's saying I expect to live another 39 years. So I guess I've reached my midpoint of my life. A little bit sad here, okay? But look, right here it's telling me the probability I would die, okay? So it's 0.002. So the probability that Matt will not live to be 40, so the probability that Matt dies is 0.002. Can anybody then tell me the probability I'll live to be 40? Well, if the probability I die is 0.002, it's 1 minus this. Okay, so 1 minus this, the probability that I'm going to live to be 40 ends up being 0.998. You have an extra 9 in there. But yes, we got close. No problem. Okay. So now that we have this, let's compute the expected value of the policy for the insurance company. Okay. So here's the thing. How much money is the insurance company charging me for this policy here? Thank you. And I appreciate the help in the chat, Melissa. Yeah, they're charging me $1,000. Okay. But now here's the thing. The life insurance policy, we're actually going to do a little bit of accounting here. Okay. The company is not going to value the policy as the $1,000. Okay. Can anybody tell me why the company would not value this as $1,000? Because they only keep $1,000 if I live, right? If I die, how much money will the company lose? Okay. So actually, this is where it gets a little tricky. They actually not necessarily lose that much money, but it's close. Okay, but they could potentially lose $250,000. Okay. All right. So they don't know. Here's the thing. When they sell me the policy, they don't know if I'm going to live or die. Like nobody knows, right? They don't know if I'm going to make it to be 40 or not. So what I'm going to do is I'm going to let the random variable X be equal to the amount of money the company makes on Matt's policy. Okay, so if I want to compute the expected value, I'm going to need to write out the probability distribution for this. Okay. So the insurance company here that sells me this policy, they only care about two things happening, okay? They only care if I live or if I die. Okay, that's all they care about. So if I make it to be 40, okay, again, knock on wood. If I make it to be 40, how much money do they make? Again. Yep, they make $1,000, $1,000. And look, we know the probability I'm going to live from the actuarial tables. It's right here. It's 0.998. All right, so now if I die, okay, I know the probability I die. It's 0.002. Okay. Now here's the thing. They're going to lose money. Okay, but they're not going to actually lose $250,000. Why would they lose that much money, Melissa? You're absolutely right.
Because you paid them the 1,000 already.
Yeah, so I paid them $1,000 already. So they already have $1,000 of my money. Okay, so if I die, my wife will get this insurance policy. And so they will cut my wife, Ashley, a check for $250,000. But I've already given them $1,000. So they're really only going to lose $249,000. All right, so now we can figure out the expected value of this policy. So mu sub x is equal to, it's the sum of the x values times their corresponding probabilities. So it's 1,000 times this. Plus this minus a lot of money, minus 249,000 times the probability I would not make it. And if you grab your trusty calculator here, you would go 1,000 times 0.998 plus minus, so minus 249,000 times 0.002. So it's a minus because they lose money. So it's the amount of money they would make, Jamie. And so if they have to pay out 249,000, they lose money, right? So that's why we put it as a negative. Okay. Yep. Yeah, no problem. And this is what the policy is worth to the company. So even though they sold it to me $1,000, there's a chance I'm not going to make it. So the long run average of them selling this policy, most people they sell the policy to is going to live. But every once in a while, someone won't make it. And so the long run average is $500. So let me ask you this. Should the company sell me the life insurance policy? Yeah, they should. They expect to make money. Anything above $1, anything above 1 cent, they should sell because in the long run they expect to make money. So they absolutely should sell me this policy. It's a good deal for the life insurance company. Okay. And trust me, whenever they go to sell a new policy, things like that, this is the type of analysis they do. They'll say, how they ask you all these questions. If you've ever purchased life insurance policy, are you a smoker? Do you have cancer? Things like that. Like it affects the probability you live or die, and so they just run the numbers to figure out how much they have to charge you so that they make money. Okay. What do you think? A little bit more interesting, hopefully, these last two examples. Well, I hope so. Not terrible. All right. Well, look, on your homework, you have a chance to practice this life insurance question. And I'm pretty sure I'll ask you one of these on the exam. Okay. So give the problem a shot on your homework. Give the problem on your homework a shot, excuse me. And setting up the problems can be a bit tricky. Yeah. Okay. Yeah, but you're right. Once you do it, it's just following a formula. All right, let's take our break. So we'll take a 10-minute break. And what I'm going to do here is I'm going to load up the other PowerPoint that I'm going to use today. And then let's come back at 2 o'clock if that's okay with everybody.
Professor, can you just put it in the other slide while we go on our break, just so I can copy it?
Yeah.
Thank you.
Is this from this page okay?
Yeah, that's perfect. Thank you.
All right, I'll see you guys in 10 minutes. Is it okay if I take this slide down? Does anybody still need it? I know I left it up there so somebody could copy it. Okay. I'll put the share back up in a second. All right, everybody, everybody ready to finish up for the afternoon? I hope so. All right. So now I want to do, I have this PowerPoint slide here that I'm just going to take a lot of notes in it. It's week 7. Can't believe how quickly the semester is going, right? We're like almost half done. Does anybody else feel like the semester's flying, or is it going really slow?
Yeah, I'm shocked. It's beyond me. But
Yeah, it's going.
hey, we're getting through this. We're getting through.
We are, yeah. And vaccines are coming. Everything's starting to look up. Weather's getting nicer. So that's good. Okay. So we're on to our last topic before we do the exam, and it's what's called the binomial probability distribution. And have out your calculator, either your TI-83 or your TI-84, as we're going to use them a bunch today. So what I'm going to do today is I'm going to introduce the topic, and I'm going to show you how to do this stuff by hand. And then during the first hour of class next time, I'm going to show you a little bit of a calculator cheat, or a calculator quick, if that's okay. But I still think it's important to just learn how to do this by hand, and then we'll go and tackle with the calculator to make things a little bit easier. Okay. So I want to introduce this concept of this binomial probability distribution with an example. And forgive me for the sports example if you don't like sports, but it's a basketball example. I think the basketball season is going on right now, right?
Yeah, March Madness is right around the corner too. Or
yes, yeah. Did Duke make the playoffs? I know that was a big thing.
not sure. They weren't really ranked this season, like along with North Carolina. So
Yeah,
I'm not really sure.
yeah. I don't follow basketball too much. I'm more of a baseball guy, and baseball season starting up, and I'm like super pumped for that. It'd be a nice distraction. And but anyways, have you guys heard of this basketball player named LeBron James? Have you guys heard of this guy? Who's that? Yeah. Right. Everyone's heard of LeBron James, right? So I want to talk about this thing in basketball called a free throw. Okay. Just out of curiosity, does anyone in here not know what a free throw is? And it's okay if you don't. I'm going to explain it regardless. But how about this? Have people heard of a free throw in basketball? People know what this is a little bit. So a few people maybe. So basically, this is all a free throws. Okay. You know, when a player goes and makes a shot or attempts a shot and it gets fouled, like the player slaps his hand or pushes him, you're not allowed to do that. They get to go to what's called a free throw line. Okay, so here's a basketball court. Here's a basketball hoop. Okay, and there's this line here, okay? And this player gets to go to the line and they get to shoot a ball with nobody guarding them. And it's called a free throw, okay? Anyways, here's the problem, okay? LeBron James makes 80% of his free throws. He's actually a little bit better than that, but I'm just rounding it way down, actually. I think he shoots like 86% or something, but I'm just going to say it's 80, okay? So LeBron James makes 80% of his free throws. So what that means is the probability that LeBron James makes his shot is 0.80, and the probability he misses is 0.20, okay? So I just have this question for you, and we're going to use this question to introduce this concept of the binomial probability distribution. If LeBron James takes 10 free throws, okay, so he's going to go to the line, okay, this free throw line, and we're going to say, all right, King James, here's the ball. You're going to shoot this free throw 10 times, okay? If LeBron James takes 10 free throws, what's the probability he makes exactly 8 of the 10? Okay. So this is what we want to do. Okay, we want to find the probability he makes exactly 8 of the 10. So there's a common mistake that sometimes happens is it goes like this. Okay, well, you know, if he makes 80% of his shots, what's the probability he's going to make 8 out of 10? Well, that's just 0.8. Okay, but that's not the answer. Okay, that would be too easy. That's not the answer. And this problem is actually really hard to solve right now. Because like there's a lot of different ways he can make 8 of the 10. Okay, like he could make his first 8, miss his last 2. He could make his first 4, miss his next 2, make his last 4. Like there's just like, how would you even go about answering this question? Okay, it's really, really hard right now. Okay, it's really, really hard to answer right now, but I'm going to show you a way to answer this question. Okay, so he's going to take 10 free throws. He's going to shoot exactly 10. We're going to give him 10 different basketballs and I'm going to shoot all 10 of them. Okay, and it's the probability that he makes exactly 8 of 10 of them. All right. So what I want to do is I want to introduce this topic, this thing called the binomial probability distribution, and then come back and answer this question for us. Okay. So everybody keep this in mind, keep LeBron James and this free throw shot in your mind, and we'll come back to it, okay? So is everybody okay if I go to the next slide? Everybody good? Okay. All right. So the binomial probability distribution. Okay, so here's the thing. This binomial probability distribution is used for what we've been working with, these discrete random variables. Okay, so let me ask you this. When LeBron James goes and shoots 10 free throws, do I know how many of the 10 he's going to make? Do I know for sure that he's going to make 8? Do I know for sure he's going to make 9? Like, do I know for sure how many he's going to make? No, I don't know. You don't. So, but here's the thing. The number of free throws he makes is going to be somewhat determined by chance because we know what percentage he makes, okay? So I'm going to define this variable. I'm going to let X be equal to the number of free throws LeBron makes in 10 shots. Okay. And what I want to find out, okay, is the probability that this X variable is equal to 8. Okay. That's our goal. I want to find the probability that it's equal to 8. And if you think about it, there's a finite number of things that could happen. Okay. If he shoots 10 free throws. Okay. So there's a finite number of outcomes. Okay. Because he could make 0, he could make 1, he could make 2, he could make 3, he could make 4, he could make 5, he could make 6, he could make 7, he could make 8, he could make 9, or he could make all 10. There's a finite number of things that could happen. Okay. And it's determined by chance. So this X here is a discrete random variable. So to be able to answer this question, because that's what we want to do, all right, I want to answer this question right here that I'm dotting around, okay? We need to use this thing called the binomial probability distribution, okay? So the binomial probability distribution is a discrete probability distribution so when I say a discrete probability distribution, it's actually going to be a formula. And that's one way we can describe a probability distribution. So this formula, okay, what it does is that describes, and when I say describes, it solves really, probabilities for experiments for which there are only 2 outcomes. Okay. So when I say there are only 2 outcomes, okay, what I mean by this is when LeBron James goes and makes a free throw or attempts a free throw, what are the only 2 things that can happen? He can either make the free throw or he does what? He either makes or misses. Thanks, Sarah. Yep, he either makes or misses. So there's only 2 outcomes. Okay, that's what I mean by this. Like looking back here, each shot, there's only 2 things. He can either make it or he can miss it, and that's it. Okay, so these outcomes are usually referred to we either refer to it as a success, or it can also be referred to as a failure. Okay, so you can have a success or a failure. So here we want LeBron James, we want to count the number of free throws he makes. So for our problem, a success is that LeBron James makes his shot, makes a free throw. And a failure is that LeBron James misses his free throw. Okay, so I'll put a little smiley face, he makes it, frowny face, he doesn't. Okay. So this distribution is going to give us a probability. So basically what I'm saying is this binomial probability distribution is going to solve this problem right here. We'll solve this problem. Okay. So now here's the thing. Not every situation that has two outcomes can be used. You can use the binomial probability distribution for. Okay. You need to meet very specific criteria to be able to use the formula I'm going to give you in a second. Okay. So is everybody, I know there was a lot on this slide to write down. Let me know, did anybody need me to stay on this slide before I go to the next one? Everybody good? Hopefully everyone's good. And we can get to figuring out this question for LeBron James. Okay. All right, so I'm going to go to the next slide. So this is the criteria for a binomial, what we call probability experiment. Criteria for a binomial probability experiment. So if you meet these four criteria, okay, you're going to be able to use this formula I give you on the next slide. Okay. So the first one here is the experiment is performed a fixed number of times. Okay, and a little bit more of this. Each repetition of the experiment is called a trial. Okay, so what do I mean by that? How many free throws did I say LeBron James is going to shoot? Like every time he's going to shoot for this experiment, how many free throws is he going to shoot? How many times does he go into the free throw line, did I say?
10.
Yep. So here's the thing. I didn't say, shoot free throws until he makes 8. That's not what I said. I said, look, he's going to shoot exactly 10 free throws. Okay. So that's a fixed number of times. He's going to the line 10 times. And so each time he shoots the ball, that's called a trial. Okay. So he's at the line 10 times and he has 10 trials to his experiment. The second thing, the trials are independent. And this is a little bit of a stretch here for our example, but what this means is, that every time LeBron James goes to the free throw line, if he makes or misses a shot, it's not going to impact the, probability he makes or misses his second shot. Okay. And this is tough, with the sports example, but we're just going to assume it to be true. Have you guys ever heard of it when they say a saying like that player's in the zone or he's on fire or he or she is on fire and they can't miss their shots. But for this example, we'll just assume, that the trials are independent. Okay. The third criteria is for each trial, there are only 2 outcomes. Okay, you either have this success or you have this failure. So, LeBron James, each shot he can only make or miss it. There's no like halvesies here, okay? And then the fourth one is the probability of success never changes. Okay, so what this is saying is, look, every time LeBron goes to the free throw line, the probability that he makes a shot, it's always 8.80. It's always 80%. He's a professional. It's just going to stay constant. Okay. So look, for this example, we're going to say that we meet this criteria. Okay, so we've got this binomial experiment with this LeBron James thing. Phenomenal. That's great. So now what we have to do is we have to now get to the formula for it. Okay. Is everybody okay if I go to the next slide? Everybody good? Got a yes. Okay. Okay. So what I want to do here is I want to give you the notation for a binomial experiment. All right, this notation is really going to help us solve this stuff by hand, okay? So when we go to do this by hand, there's going to be 5 numbers, okay? 5 numbers you're going to need to plug into a formula, okay? I know it seems like a lot, but you're going to have to take 5 numbers and plug them in, okay? And here are the numbers that you're going to see on the formula that comes up. The first one is we're going to let n equal the number of trials, okay? So how many free throws was LeBron James going to shoot?
Ten.
Yep. So what's going on here is the number of trials is 10. Okay, for our example. The second thing is we're going to let x be equal to the number of successes. Okay. So how many free throws did I want King James to make?
8.
Yep. So x is 8 for our example. By extension, does anybody know what n minus x is equal to then? If n is the number of trials and x is the number of successes, does anybody know what n minus x would be?
10 minus 8.
Yep, which would be the number of not successes, but
Failed attempts.
failures. Yep. So I want LeBron James to miss 2. I want him to miss 2 free throws. Then the fourth notation, we're going to let the value P be equal to the probability of success. Well, what's the probability I said LeBron makes a free throw? Was it that on the screen there? Everybody can still hear me, right?
Yeah.
Yeah. Okay. So that's the probability of success for LeBron James looking back. And then the final one is if P is the probability of success, does anybody know what 1 minus P is? It would be the probability of what?
Failure.
Mm-hmm. So the probability that LeBron James is going to miss a free throw is going to be 0.20. Okay. So now we're actually, I'm going to just save it on this slide here. I'm actually going to give you the formula here, just so you can see it next to all of this. Okay. And the formula just goes like this, okay? For a binomial experiment, okay, with probability of success P, the probability of obtaining X successes in N trials is given by. Okay. So this first notation is going to seem weird. It's the probability that X is equal to X. Okay. And so what that means for our example, it's the probability that X, the number of successes, is equal to 8. So LeBron James is going to make 8 of the 10 free throws. Okay, so the first thing you have to do in this formula is you have to figure out the number of different ways LeBron James can make 8 free throws in 10. So that sounds kind of like an N and R problem. Do you guys remember when we were talking about permutations and combinations? Okay. So I want to figure out, I want to count the number of ways LeBron James can make 8 of 10 free throws. So the question I have to ask you is this: do you think I care about the order that LeBron James makes the 8 free throws, or do I just want him to make 8? Yeah, so does order matter or order not matter?
Not matter.
Yeah, so it's a combinations. So the first thing you have to do is you have to do N choose X, okay? So for our LeBron James example, I have 10 free throws and I want to choose 8 of them, okay? Then you're going to multiply that by the probability of success, P, raised to the number of successes. So I'm going to multiply 10 choose 8 by the probability of success, 0.80, and I want LeBron James to make 8 free throws. And then I need to multiply that by the probability of failure, 1 minus P, raised to the number of failures. So 1 minus P here is 0.20. And I want LeBron James to miss 2 free throws. And that's your formula right there. So what we just need to do now is we just need to figure out what this crazy thing is equal to, okay? So look, does it look a little daunting here? You know, be honest. Does this formula with my mouse going over, does it look a little crazy? Yeah, sure. But I promise you this, like the formula doesn't change. So like all you have to do is figure out these 5 things and then you just, it's a plug and chug. Plug it into the formula and chug through the answer, okay? So let's figure out the probability then that LeBron James would make 8 of his 10. All right, so let's grab our trusty calculators. I'm going to do this on the TI-83. But if you have a TI-84, it's the same process, okay? So let's figure out what 10 choose 8 is. So I'm going to go 10. I'm going to click my math button. I'm going to go over to PRB or PROB. I'm going to go down to N choose R. So it looks like there's 45 different ways. That's crazy. 45 different ways that LeBron James could make 8 of his 10. Okay. 45 different ways. So the next thing I need to do is I need to multiply it by 0.80. So I'm going to just hit times 0.80 raised to the 8th power. So I'm going to press this little caret sign to raise it to the 8th power. And you should get this. And then I need to multiply that by 0.20 squared, or raised to the 2nd power. And that's my answer right there. Did anybody following along with me get that?
It's a little confused, but yeah, I got it.
Okay, so it's 0. I'm going to go to 3 decimal places here. So it's 0.302. So this is crazy. So even though he makes 80% of his free throws, the probability that he goes to the free throw line and shoots 10, the probability that he'll make exactly 8, even though he makes 80% of them, it's only like 30%. It's a little over 30%. So, you know, the reason it's like that is because he could make 7, he could make 9, he could make all 10, he could only make 6. Like, there's all these other things that could happen. So even though, you know, he had, you know, the probability that he'll make 8 of the 10, even though he makes it 80% of the time, it's really only 0.30. Okay. How about I stick with this example, but I ask 2 follow-up questions, and then that'll take us maybe 10, 15 minutes, and then we'll call it for the day. Okay. Sound good? I hope it sounds good. Okay. Is everybody okay if I go to the next slide?
Yes.
Good. Everybody okay? All right. So keep this in mind. We're going to stick with this LeBron James example. Okay. So I'm just going to rewrite the formula up here. Okay. So the probability that you get X successes is N choose X times P to the X times 1 minus P to the N minus X. Okie dokie. All right. So here's the next question. Again, LeBron James is going to shoot 10 free throws. What's the probability LeBron makes 8 or more of the 10? Okay. So it'd be the probability that X, the number of free throws he makes, is greater than or equal to 8. Greater than or equal to 8. So you just have to figure out a way to solve this, okay? So if I want 8 or more, I could have X is equal to 8. He could make 8 free throws, or how many could he make of the 10? If I want 8 or more, does 9 count? Yep. Or you could make all 10. All right, so check this out. Look, I've got the probability of X is equal to 8, or X is equal to 9, or X is equal to 10. When you see the or statement in probability, what mathematical operator does that imply? Not multiplication, that's the and statement.
Addition.
It's addition. Yep. That's okay. So it's probability that X is equal to 8 plus probability X is equal to 9 plus probability X is equal to 10. I've got good news, bad news, okay? The good news is, did we actually just solve this on the previous slide, this X is equal to 8? Yeah, right. We saw that just going back, the probability that X is equal to 8 is 0.302. So what I now need to do is figure out these two. Okay, I need to figure out these two. Okay. So look, it's just n choose x, okay? So he's going to shoot 10 free throws. I want him to make 9 of them because now it's x is equal to 9 times, what was the probability LeBron James makes a free throw?
0.80.
But now look, raised to the x. Well, now x is now 9, raised to the 9 power, times probability of failure. In this case, now n minus x. This is 10 minus 9, which is 1. So now just watch my calculator. So we're going to do 10, choose 9, times 0.80 to the 9th power, times 0.20 to the first power, which is just 0.20, but look, it's 0.268 now. So it goes down a little bit. So 0.268 when I round it. So I've got this. So now what I need to figure out is the probability that he's going to make all 10. So it's n choose x. Well, now in this case, this is 10 choose 10, and that's okay, times probability of success raised to the x power. Well, now I want him to make all 10 times probability of failure now in this case, what is n minus x if I want him to make all 10? How many failures do I want him to get?
0.
And that's okay. And that's okay. I'll help you out a little. 10 choose 10 is actually just equal to 1. 0 times 0.80 to the 10th power. And does anybody know what 0.20 to the 0 power is? Does anyone know? Yep, anything raised to the 0 power is just 1. So this problem is actually just 0.80 to the 10th power. And this one looks like it's 0.107. Okay. All right, so now I can figure this out. Now I can add all of these up. So the probability that LeBron James, he would go to the free throw line and he would, he's going to make, 8 or more. It's 0.677. Did anybody else get that?
Yes.
Did I do that right? Okay, so 0.677. Which is not bad. Which is not bad for the second best basketball player of all time. Okay. Anyone know who the first best player is?
Definitely Michael Jordan.
Definitely. I mean, come on. It's Michael Jordan. No question in my mind. Okay. All right. Let me just ask one quick follow-up question to this, and then I'm going to just talk about, do people feel like a little overwhelmed with this formula? Just be honest. Does this formula seem like a little overwhelming?
Yes.
It's okay. And so I'm going to be honest with you. The reason I went through this so quick is it's okay if you shake on it, no problem. There's obviously an easier way to do this. Okay. And I'm going to show you, I don't have time in class today, but I'm going to show you how to do this on your graphing calculator next time. So I really just wanted to chug through the formula here just so you can see what's going on in the background. And then I'm going to show you next class how to use your calculator. So just a quick follow-up to this. So we saw the probability that he makes exactly 8, probability that he makes 8 or more. So the next question here, what's the probability LeBron makes 7 or less? So it's the probability that X is less than or equal to 7. Okay. So there's a hard way to do this and an easy way to do this. Okay. The hard way to do this would be probability X is equal to 0 plus X is equal to 1 plus X is equal to 2 plus X is equal to 3 plus X is equal to 4 plus X is equal to 5 plus X is equal to 6 plus X is equal to 7. But can anybody offer me a little bit easier way that I can do this really, really quickly? Well, what's the complement to 7 or less? It's 8 or more. Okay. So the probability that X is less than or equal to 7 is equal to 1 minus the complement, which is X is greater than or equal to 8, which is what we just found here. So it's 1 minus 0.677. Which would be 0.0323, I believe. Okay. I just want to show you one last thing before we end class, okay? On your homework and on your exam, I'm not going to ask you to chug through these formulas like this. Okay, this was just doing it by hand. But if you grab your calculator, it doesn't matter if it's a TI-83 or a TI-84. I just want to just verify something real quick. Yep. Okay. Does everybody, if you have your calculator, does everybody see this button called DISTR, this blue thing or yellow thing over here that's called DISTR? Do you guys see that? Okay. So everybody hits second function DISTR. So second function DISTR. Now we are going to use this distribution option in our calculator a ton. You're going to get so sick of it during the second half of class. I'm sorry. But if you scroll down on your calculator till you get to this A and B on your calculator, do you guys see this thing called Binomial PDF and Binomial CDF? How many people see that?
Professor, I'm sorry, but how do you get to where you are on the calculator? I have the TI-84.
TI-84, okay. So you hit the second function button here, and then do you see DISTR? Where my mouse is?
Second function.
That wasn't what I asked. So I asked, did you see the DISTR where my mouse is?
Oh, yes, I do.
Yeah. So you hit second function and then just press the vars button.
I do.
And then do you see this?
Yes, I did.
Awesome. Now scroll down
Thank
to,
you.
Yep, no problem. All right, so you see these options called Binomial PDF and Binomial CDF, everybody? People see those? Well, this was a binomial probability experiment, okay? So I'm going to show you something on your calculator. And if you have the TI-83, it's a little bit harder, but I'll cover that next class. Look here, the probability that we said LeBron makes 8 of the 10 was 0.320. So watch this on the TI-84. I'm going to use this first option A. I'll explain what binomial CDF is next time. And look what comes up. It says the trials were 10. P is the probability of success, 0.80. And how many successes did I want? I wanted 8. Look. Do you guys see it's the same answer? Okay. Was the calculator, I know I just blew through the calculator, so we're going to spend a lot of time on it, but like, does this calculator option seem a lot easier than doing it by hand?
What?
Yeah. Yeah. So what we're going to do next time is I'm just going to teach you, we're going to do like 2 examples, 3 examples of using this calculator just so you can see how to set it up. And we won't stress about the formula anymore. Okay, we're going to jump right to the calculator for this. I know everyone's thinking, Matt, why didn't you just do that to start? Right? Is that what everybody's thinking? Maybe not. Maybe people don't want to answer. Yeah, no comment. Fair enough. Fair enough. All right, everybody. So we'll
Professor?
yeah.
My calculator didn't like have that little chart that you'd had.
Do you have
Like,
the
I don't know
TI?
why.
Do you have the TI-83?
I have the TI-84.
Okay, and did it just go binom PDF and then parentheses?
Yeah.
Yeah, I'll show you how to do that next class. So it's a little bit what you had to do if your calculator showed you this. You just had to go 10, the number of trials, common number, probability of success, and then the number of successes. Like you just have to remember to put that in. And I'll go through that next time. Okay. So you don't have to like, don't stress if I just blew through that really quickly. Like we're just gonna spend a lot of time on Thursday doing that. Okay. So don't worry if your calculator showed that instead. All right. Sound good?
Sounds good.
Okay. So I believe I forgot to put up the recording last time. So I put it up today. What I'm going to do now is I'm going to, I'll post the, I'll post it to YouTube and I'll try to remember to put it in the classroom before I end my work day for the day. Okay. So unless there's any other final last minute questions, I guess I will talk to you all on Thursday. Sound okay, everybody?
Sounds good.
Okay.
What's brown?